Being at CppCon has been amazing because you can directly speak with the experts. I've had conversations with Bjorn Strusepp, with Sean Parent, and they're all very friendly and accessible and willing to give their opinions or advice on C++.
Learning is a funny thing. I find that when learning, the materials we learn from tend to go too far one way or the other. They tend to spend too much time on theory or too much time on the practical effects. For a confirmation of this, just talk to any university student and hear them talk about how they spend their days trapped in a lecture hall receiving pure theory. Little of what they learn appertains to the real world. But we see this in software engineering as well. When we check the documentation for a new technique or framework or library, we tend to find small, fully worked examples. They demonstrate the fancy features, but how do we take those and build large-scale software systems with them? Or we get just API documentation, the small pieces we're supposed to compose, but how do we iteratively compose them and finally reach a high-level artifact? And so what I want to do is take you on a tour through an application built with the networking TS, from the lowest level all the way up to the highest level, and eventually build a real application that listens on real sockets for real connections from real users on a real network. But first, we need our scenario. We need our use case. And so what we want to build is a part of a larger system that receives queries from clients and returns to them market data. We're not streaming live multicast data. Instead, we're answering targeted queries which arrive over HTTP or WebSockets. These heterogeneous queries are received by a front-end component we call a router, which looks at the queries and decides which backend should service them. It's this backend we're interested in. It communicates with the backend using a proprietary protocol. And the backend is implemented using the networking TS, using Boost ASIO. It's implemented on top of a proprietary in-house file-based time series database. And so not only are we going to see the asynchronous domain of networking, but we're going to see how that interoperates with the synchronous non-blocking nature of file I/O. But what about that proprietary protocol? What about the language we're going to try and teach the networking TS to teach Boost ASIO to speak? This protocol is called DataCon and was designed by a coworker of mine. Being designed only for internal communication, we have, at least for now, foregone things like authentication or encryption. We're interested in keeping our latencies low and keeping our throughputs high. This protocol supports a rudimentary request-response cycle. The client, in the DataCon sense, which is that router talking to our final client, submits a request to us, we accept or reject, and then we send the response. But we don't just send the response, we stream the response. Because part of our use case is supporting responses that are so large they can't possibly be buffered in memory. We want to be able to deliver responses to users that are many gigabytes or even terabytes. And because we're interested in latency and throughput, we provide utilities for the front end, for the router, to reuse the back-end connection, to cancel responses they no longer need, and to keep idle connections active, not just so the front end can connection pool, but also in case we have a query which might go idle for some time. You might imagine a user who wants to follow live market data as it's coming in, wants to open a query and receive ticks all the way through to the end of the day. And that symbol may not tick for a while, and so the server may need to send a heartbeat to keep the connection open, to figure out if that pipe is broken. Now that we've motivated our use case, let's take a look at the actual bytes we're going to be sending. Let's take a look at how the DataCon protocol looks on the wire. Every DataCon message starts with a 5-byte header, the first 4 bytes of which are the little-endian unsigned length of the entire message in bytes. Therefore, we have a minimum value here of 5. Thereafter, we have a single byte, which discriminates the semantic purpose of this message in the DataCon protocol. And after that, we have a free-form body of bytes, proceeding from the 5th byte until the end of the message identified by the length. It's important to understand that this is a free-form body of bytes. The meaning of these bytes is completely application-specific. This protocol's only job is to communicate request-response semantics and to provide pipelines for the application-specific data about requests and embedded in responses to flow between client and server. But this discriminant, this message type, implies there's a datacon vocabulary. It implies there's some language that is being spoken, for example, from the client to the server. And the vocabulary from the client to the server consists of 2 messages. The first, the most obvious of which, is the request, which transmits a request from the client to the server and has a payload of application-specific bytes which describe the request the client wants executed. Beyond that, of course, the client needs a way to end responses early, and so they have a cancel message with no payload, which requests that the server end the response and return to the idle state, ready for another request as soon as possible. Which leaves us with the larger vocabulary the server speaks to the client. The server, of course, needs a way to acknowledge and reject requests. And when it acknowledges requests, it sends a payload of application-specific bytes, which describe the response which is to follow. You can imagine an application which realizes this by transmitting the MIME type of the response. It says application/JSON, for example. The reject request, on the other hand, has an application-specific payload which describes why the client is being rejected. And this message has a new property. It's terminal. When the client receives this message, they know the connection has transitioned back to the idle state. They know that the response they tried to set in motion is now over and that they can send a request anew. Which brings us to actually transmitting that response. And for that, we have 3 messages. The first is intermediate chunk, which just transmits some part of that response, some application-specific payload. Another part will follow. The final chunk does the same thing, but has the additional semantic that the response is now done. That this is the last piece of data in the stream which is in response to the request. But this streaming formulation, this idea that we can't buffer the entire response in memory when we decide to accept it, means that maybe as we're processing our response, we run into some error. There's some unforeseen circumstance which prevents us from fully answering the client. And so we can also send an error with a payload which describes the error in an application-specific way and which is terminal, which brings the connection back to idle. Which leaves us with acknowledge cancel, which is sent when a cancel is received and the server commits to sending no more of the canceled response. And then, of course, we have that heartbeat, which has no payload and is not terminal, which is just sent during periods of inactivity. So now that we understand the vocabulary, we understand the structure of the messages, and we understand the use case, let's take a look at how we're going to start designing our implementation. Let's see how it is we can teach the networking TS to read datacon. And so we begin with an enumeration of all of the message types because we don't like magic constants in our code. Note that we also throw in unknown in case, for some reason, we need to represent something like a parse error. Which brings us to the initiating function for the async read operation. The operation which will read exactly one datacon message from some async read stream, the first parameter to the initiating function. And then we give it something called a dynamic buffer, which it's going to use to read into, and we inject a completion token that the operation can use to report back to us that it's done. But in previous years, when I've given talks about the networking TS, I've talked about const buffer sequences and mutable buffer sequences, but never dynamic buffers. So what is this named type requirement? What is this parameter, and what does it represent? Well, unlike in previous years, we don't know exactly how many bytes we want to read before we start out. We need to read the header to figure out exactly how many bytes to read. But once we've read the header, our read operation is started, the storage has already been injected, and now there's no more customization point if we were just using a mutable buffer sequence. And so we need something that's akin to a const or mutable buffer sequence, except it's not just a handle to some view of bytes, but is rather a handle to a view of bytes and an allocation strategy, some way of resizing that buffer. And so it has embedded type aliases, const buffers type and mutable buffers type, giving the const and mutable buffer sequences it will use as its vocabulary. Then it has 3 getters, which should be Familiar to anyone who's ever used a standard container: size, max size, and capacity. Then we have two observers, const and immutable overload, which allow us to actually get views of the backing storage, views of those bytes the dynamic buffer handle is managing. The first parameter indicates the offset from the beginning at which the view should begin, and n indicates the number of bytes which that view should be a view of. Which leaves us with the three most interesting functions. Grow, which tries to add n bytes to the end of the underlying storage and throws std length error if it cannot. Shrink, which removes n bytes from the end, and consume, which removes n bytes from the beginning. But I said something very disturbing when I introduced this slide. I laid out the motivation for this class, and part of that motivation was that when we start reading, we don't know how many bytes we need to read. We need to read something off the network to figure out how many bytes we need to buffer. But who's to say that our peer is trustworthy in this regard? Who's to say they aren't just going to send us 4 bytes with all the bits set to 1? That would cause us to go off and allocate 4.2 gigabytes of memory, and then they could just turn around and do the same thing over and over again. Eventually, the Linux kernel is going to wander by, the killer is going to wake up, our application is going to die, and we're going to deny service to all of our clients. But dynamic buffer is a named type requirement. We can inject any type that models the requirements. And we saw there was a max size member. And so maybe we inject a type that customizes that max size member to constrain the allocation that can be performed. But when grow runs into the max size, it throws std length error. This is not how errors are idiomatically reported in the networking TS. Throwing an exception will cause it to just bubble up into the execution context, be re-emitted in main, and cause the application to die. But that's exactly the problem we were trying to solve. That's the scenario we were trying to avoid. But max size is still sitting there. It's part of a policy about memory allocation that we're having injected into us. It's oh so promising. And so what I've done in the implementation of async read is I've regarded it as a policy. I have an enumeration of all the errors async read can emit, and only the relevant ones are there on the slide. Max size too short for header, in the case that max size is too short for me to allocate even space for the header, 5 bytes. Max size too short for payload as well, in case the max size is too short for me to subsequently allocate space for the payload. Then I have a make error code factory function, which can be found via ADL, which coalesces an enumerator into an std error code. And then I have this helper function, async read grow, which in the actual code is embedded in a detail namespace. It takes in the buffer it wants to grow, the number of bytes it wants to add, and the enumerator representing the appropriate error to return if it can't. It goes off, it grabs the max size, and it does overflow-resistant arithmetic to see if the request would overflow the max size. If it would, it returns an appropriate error code. It returns a truthy error code. This causes the underlying operation, async read, to end in error. It causes that error to bubble up through all of the subsequent asynchronous operations and to be emitted at the highest level, to be emitted in the connection management layer of the server. Where the connection is seen to have ended in error, it's reaped, and the server continues on happily. Which leaves us with the happy path, in which case we just grow the buffer by n bytes and return a default constructed error code which indicates success. This, of course, is the most likely path. But in talking about async read, I've omitted something else, because async read is the initiating function of an asynchronous operation. And asynchronous operations don't complete by reporting their values through the return channel. No. They complete later. They invoke a completion handler, and as such, they have a completion signature. So the completion signature of async read contains an error code, the number of bytes transferred, the message type which was read, and a view into our dynamic buffer. Which raises questions about why exactly these 4 values were chosen. After all, if the user is injecting into us intelligence about how to allocate storage, if they control the view of that storage, why do they need to know how many bytes transferred? They should know that implicitly based on how much space I allocated. And why do I need to give them a view of the payload? Why don't I simply manipulate the dynamic buffer until it only contains the payload, and then they can go off and inspect it? But I synthesized all this context in the operation. I know exactly how many bytes I transferred, and I know the exact bytes in the dynamic buffer that represent the payload. So why would I assume the user doesn't need them? Why would I drop them on the floor? Why would I leave the user poking around at bits they injected and in an error-prone way trying to resynthesize information I already had? And most importantly, perhaps, why would I consume the header off the beginning of the dynamic buffer? Why would I pay to shift all the bytes in the buffer when I know the most common use case of the user is going to be to look at the view of the payload, process it, clear the buffer in big O of 1, and start reading again? But this design, this low-level function, is only half of the equation. Because it only lets us read datacon, it doesn't let us write it. And so to write datacon, I have a type alias async write state for an array of 5 bytes, somewhere to prepare the header so I can pass a pointer thereto to the operating system to transfer it. Then the completion signature for async write is an error code indicating the status of the operation and the number of bytes transferred. As for the signature of the initiating function, I accept the write stream, I accept the message type to write, I accept a stable reference to the async write state to use to prepare the header, a view of the payload I'm going to send, and of course, the completion token I use to notify my user of completion. But why am I making my user responsible for maintaining the lifetime of this async write state? That seems like an implementation detail. Why don't I do that myself internally? Well, for one, the user may want to inspect that state. They may want to know the exact bytes that were placed in the header so they can use them for some purpose. I shouldn't assume that's not part of their use case. And then internally to my operation, if I need to create a stable async write state, I need to pay to allocate it. But my user's already keeping things alive for me. They're keeping that stream alive, and they're keeping whatever bytes that buffer is a view of alive. So they have some stable state, and so I allow them to inject the async write state. I allow full context to flow out of my asynchronous operation, and I don't make my user pay for allocations they don't need. But these are just 2 very low-level building blocks. They aren't that high-level application we were promised, and that's because building an application using the networking TS works just like this. We build very low-level components, and we build our way up. And this isn't just philosophical. This has real-world benefits. When I was writing this server, when I was decomposing it so it wasn't a monolith, I had occasion to need a datacon command line protocol debugger, something for functional testing. And if I'd embedded all of these operations directly in a monolithic server, I would have had to go and resynthesize them and hope that I did it correctly twice instead of just once. But because I was building an ecosystem rather than a monolith, I could just take these 2 operations, write 150 lines of code, and I had a fully working protocol debugger. But that doesn't get us off the hook. The point of this talk is not to write low-level operations. Everyone who's watched my previous talks knows how to do that. So let's figure out how we can send those heartbeats, how we can keep the connection alive, how we can implement some of the higher-level requirements of the datacon protocol. And the first thing we see here is this reason enumeration, with enumerators wait and write. And the impetus for this is that a heartbeat operation needs to wait on a timer and write to a stream. And when it emits an error code when it fails, it could have come from either of those operations. But it knew which of those operations it came from, and so it doesn't need to just emit an opaque error code. It can also give us the exact reason, whether it failed waiting or writing. But there's something suspicious about this enumeration. It gives us the 2 possible sources of failure, but what about the third option? What about success? And the omission of that enumerator is deliberate, because the operation that you see initiated by the initiating function at the bottom of the slide never succeeds. Because this operation is not about sending a heartbeat and waiting for some amount of time. This operation is about dealing with the entire problem of sending heartbeats over the lifetime of the entire datacon connection. And as we all know, if we've written some network programs, connections don't end successfully. The connection is reset, we reach end of file, we write to a broken pipe. And so this operation, once initiated, goes off in the background. It sends heartbeats and it waits over and over and over again until the connection is done. And when it finishes, it emits a statistics struct, which contains a counter of how many times it did various things. And I've wrapped these things in a structure rather than making them individual arguments in the completion signature because I may want to extend it later. I may want to add some new members, and I don't want to break all of my users when I do so. Which brings us to the initiating function of our asynchronous operation, which always fails. It takes in a write stream, because it's going to write those heartbeats, a write state so it can prepare the header, a waitable timer to wait on, something called an event structure, and of course the completion token it's going to use to notify the caller when we inevitably fail, with the reason for that failure and the statistic structure. But what's that events object? What's the motivation for that? Well, the issue with writing these kinds of very long-lived, very high-level asynchronous operations is there's 2 or 3 little tiny knobs, little tiny bits of logic your user's going to want to customize. They're going to want to inject. And the event structure wraps that up in a named type requirement. It exposes to the user the ability to customize those parts of the operation that depend on the embedding of the operation, that depend on their system, that depend on components we don't want to couple ourselves to. So let's take a look at that name type requirement. Let's take a look at the logic that can be injected into our async heartbeat operation. Heartbeat events is very simple. It has a null array function delay, which when called tells the heartbeat loop how long to rest for. And this is because we don't want to just send heartbeats every 5 seconds, for example. We want to send heartbeats often enough that the connection is never inactive for more than 5 seconds. And some other component may have caused there to be activity on the socket. And so we need to have intelligence about that injected through this events object. Of course, if 0 is returned, it means the connection is currently inactive. The heartbeat function should go off and send a heartbeat. Which brings us to that second function, motivated by that formulation. There are going to be other components of this system sending to the stream. Of course there are. A datacon connection is not just about keeping it alive with heartbeats. There's other things we want to do with it. And so once delay returns 0, and tells the heartbeat operation it's good to go off and write a heartbeat, it needs to tell the underlying component that it's finished writing. So the underlying component can manage the stream being shared. Because if 2 operations try and write to the same stream, it's thread safe, but the writes may end up interleaved. You may end up writing things that aren't even valid datacon. But as I just said, this is just writing heartbeats. This is just keeping the connection alive. How can we actually implement the high-level semantics of datacon? How can we implement this state transition diagram, which describes what datacon is actually meant to do? Receive requests and transmit responses. But as we look at all the edges in this state diagram, we notice something interesting. Earlier on in the talk, when I was talking about the ability to reuse datacon connections, I said they went idle. And there's an idle state on that state transition diagram. But when we send the final chunk, we don't go there. We go to something that's called after response. And what's the deal with this state? What does it mean? An after response is a reification of something that doesn't just occur in networking, but which physicists know is endemic to reality itself. Information takes time to propagate. It is not transmitted instantaneously. And so keeping the state of 2 machines removed by some physical distance in perfect sync is utterly impossible. Imagine the following scenario. We have a datacon connection humming along, sending the response from the server to the client to some request. The client, all of a sudden, decides it doesn't need the response anymore. And so it sends a cancel message. It sends it sailing across the network. But in the interim, as those bytes are flying across the network, the server generates the final chunk. The server sends the final chunk and it goes back to the idle state. Then, sometime later, that cancel message arrives, but there's no response to cancel. This seems like a protocol violation. You're trying to cancel a response when there isn't one at all. But the client had no way of divining this information. The client had no way to understand that by the time the cancel arrived, the response was already going to be done. And so we introduce this state. We introduce after response in order to deal with this fact that's endemic in reality, that information takes time to propagate, that states can't be perfectly synced. And in so doing, we find ourselves in good company. Because TCP contains states that have similar motivation. The states close wait and time wait. Now that we understand that state diagram, let's actually try and reify it in an operation that will abstract all those complexities away. We begin with a reason enumeration, which is rapidly becoming an idiom, and a statistic structure, which is also becoming an idiom. Then we have the initiating function for our asynchronous operation. It takes in a stream, not a read or write stream, because it's going to both read and write messages, a dynamic buffer to manage its reads, an event structure, which we'll explore in a moment, and a completion token through which it reports its completion. An error code, always failure, because just like heartbeats, this deals with the problem across the entire lifetime of a connection, and a statistic structure, which is a summary of what it did and why it failed. So let's take a look at the control events. Let's take a look at the customization points that the control operation has. First of all, it has complete write because it needs to write, and so it needs to coordinate that with other parts of the system sharing the socket. Then, because it can generate cancel signals coming in from the user, it has a cancel function that it uses to report to the implementation that whatever query is currently running should stop as soon as possible. And then, because the whole purpose of async control is to get us requests so we can service them, it has an init function that it uses to initialize the underlying subsystem. It passes in a const buffer sequence, which is a view across the application-specific payload of that request. But what does this return? This needs to be able to signal to us that we should reject or accept. And in either case, it needs to be able to give us some application-specific data which should be sent alongside that accept or reject. And so we turn around and we embed this formulation in the C++ type system. We have two types, one called async control accept and one called async control reject, and each of them contains a const buffer sequence. Note that the const buffer sequence is a view. It's not some allocated type because we take on the responsibility as implementers of this events class of managing memory. We do so for the same reasons we do it with dynamic buffer. We don't want to couple async control to a single arbitrarily chosen way of managing memory and keeping it alive. Instead, we want to put that decision where it belongs, on our user. We want to maximize the reusability of our operation. Now that we have these two types, we need to wrap them up somehow because the C++ type system doesn't allow us to return two heterogeneous types. Unless, of course, we wrap them in a variant, and so that's exactly what we do. But accept and reject aren't really the only outcomes that we can imagine. We can imagine initialization encountering an error so bad that the entire connection needs to wind down, that the query underlying this needs to be destroyed. And so we add a third alternative. We add error code. But then we remember that this whole system is acting as a bridge between the asynchronous domain and what's fundamentally the non-blocking domain. And so we add an additional semantic as well. If that error code alternative is selected, if it's truthy, and if it represents operation in progress, the async control operation will decide that initialization isn't finished yet. It's not ready. It'll go off and call us again later. Which brings us to the bottom half of async control events. Which brings us to the final things we need to inject to actually get this operation off the ground. The first of these is async start write. Which is interesting because now we've moved beyond injecting synchronous callbacks, fundamentally, into an asynchronous operation. Now we're injecting asynchronous callbacks into an asynchronous operation. Because unlike async heartbeat, which could just say, oh, okay, I can't write now, I guess I'll write later, because its whole job is to keep the connection active, and if someone else is writing, the connection is definitionally active. The things that async control needs to write are really important. We can't just say, okay, try again later. And so we need an asynchronous operation that waits for the next time we can write, which gives us an async write state that we can use to prepare our header, and which obligates us to come back and call complete write when we're done. But more than this, once we've initialized the underlying component, we need some way to tell it that it can go off and it can send the body of the response, that it can send all those intermediate chunks, and finally, the final chunk. And so we have an async run injected operation for this, which reports completion with an error code and some implementation-defined statistic structure. All async control depends on is that it can pick several named members out of this to combine it into its higher-level statistics. And then we have async wait. Because async control needs to be able to poll to initialize those non-blocking implementations, and so it needs an injection of some intelligence about how long it should wait and when and why. And rather than just blithely injecting some duration, we put maximal control in the hands of our users. They get to decide how long. They get to decide how that wait will be realized. They can manage that component. But this brings us to something interesting. This brings us back to one of the fundamental guarantees that asynchronous operation gives us, and that is non-reentrancy. In the networking TS model, when you initiate an asynchronous operation, you're guaranteed the completion handler will never be invoked below that initiating function on the call stack. Because if that was allowed, reading from an always ready pipe would rapidly cause a stack overflow. You'd initiate a read and it would be completed, and then you'd initiate another read below the initiation of the first read, and so on and so forth. And while that makes sense in the domain of asynchronous operations meant to be published as consumable bits by consumers, what about when we're injecting asynchronous operations? We're injecting asynchronous callbacks into something that is itself an asynchronous operation that already has to offer this guarantee. And so we may waive this requirement. And if we think about async start write, it becomes obvious why we can and should do so. If async control initiates async start write, and the socket is immediately available for writing, and we invoke the completion handler immediately, then async control is just going to start an async write, an asynchronous operation which offers the reentrancy guarantee. And so all we would be doing by demanding that async start write behave like a proper asynchronous operation in this instance would be unnecessarily eating up performance, something that we as C++ developers don't like to do. Which brings us to the lower level, which underlies both of these high-level asynchronous operations. The query driver, which actually manages the components of the system and manages the query. Of course, it has a reason and a statistic structure. This is getting old by now. But it also has a setting structure, which is a structure for the same reason statistic structures are structures. If I want to add settings later, I don't want to break all of my users by changing a bunch of function signatures. And so we look at the design of the query driver, and it's templated on a write stream, a waitable timer, and a query. And for its internal stream, the type that it actually uses, it uses a sticky cancel async stream. And this is to solve a problem that's endemic in cancellation. When you go to cancel an operation, the operation may already have completed. Its completion handler may be awaiting invocation. And then when the completion handler is invoked, it's unaware it was canceled and keeps on going like nothing happened. As I discussed in my talk 2 years ago, a sticky cancel async stream preserves the cancellation. It makes it sticky. Subsequent attempts to initiate an operation will result in that operation failing immediately and reporting that it was canceled. Which brings us to our constructor, which takes the usual suspects, and a getter for the query object we're actually managing. Then we have 3 functions which we're going to need to implement the glue between this and async heartbeat. We need to figure out when the last write happened, we need to be able to synchronously try and start writing, and we need to be able to report that writing completed. Which leaves us just with the hooks that we need to glue async control on top. We need to be able to ask whatever query we're driving to cancel itself. We need to manage the async heartbeat and async control events together in when they can and can't write, and so we have an async start write in addition to the synchronous alternative we saw in the previous slide. Then we have async run, which goes off and implements the actual logic of running that query object that we're wrapping. And we have async wait, which makes use of some internal timer to enable polling. Which raises one final question. What does a query look like? What does this small nugget of functionality that we spent all this time wrapping up look like? What is the glue that the final user who actually wants to implement that application-specific query have to do? And here it is. It has an associated enumeration, which is wait, payload, error, and complete, which are the various statuses you can get back when you try and synchronously run a query. Wait invokes that non-blocking behavior of please try again later. Payload indicates that some bytes have been generated and are ready to be sent. Error indicates that it can't go on. The entire query needs to end. And complete indicates that it's finally done. As for the named type requirement of a query itself, we of course have a way to initialize ourselves based on a const buffer sequence. We have a way to perform an incremental bit of work we call run, which returns a query status. And because we can be canceled and we want to recycle this object, we have an end function which is called and tell us that we should get ready to be initialized again. Then, since run has no pathway to give us the payload that we're managing internally, we have a payload getter. Which brings us to this function called toggle. And the fact that we have a function called toggle is actually an artifact of the fact that my academic background is in graphics processing. Because if we think about the cycle of a query, we call run, we generate a payload, and then we send the payload. And as we discussed earlier, network operations take time. That's why they're asynchronous to begin with. But do I really want to leave the CPU and hard drive idle while I wait for this network operation to complete? And once the network operation completes and I come back and I'm rerunning the query, do I want the network to wait for the CPU and hard disk? And so what we do is when we call run, we generate the response into the front buffer. And then we grab a view of it with the payload getter and we call toggle, which demotes the front buffer to the back buffer and promotes this back buffer to the front buffer. Then we can go off and we can send from the back buffer while simultaneously calling run to generate additional bytes into the front buffer. Not only does this keep the network and the CPU and the hard disk maximally busy, but the fact that all we're doing is rotating between two buffers means that at some point in our connection, we'll generate the biggest payload we're ever going to generate. We'll allocate enough memory to store it, and then we'll never allocate again. All we'll do is the query runs and is reused over and over again by the connection is just swap two pointers back and forth. Which means we've implemented all of this, or at least designed it. There's some glue in there. There's the query driver async heartbeat events and async control events ref that we haven't looked at, but those are very trivial classes. Those are classes where I just implemented a name type requirement and each one of them was implemented by looking through a reference and calling some member function. But this only handles a connection. And I promised you a server. And servers need to accept connections. And servers need to find somewhere for the work associated with a connection to run. And so we still have more work to do. We have more pieces of this puzzle to look at. And so let's see how we abstract away accepting incoming connections. We do so with another of this family of operations which never succeeds. When we kick off async accept, we give it our acceptor. We give it a stable piece of memory to record the remote endpoint of the socket accepted. We give it some event structure and a completion token through which it reports completion by way of a failure in the number of sockets accepted. We're handling the problem of accepting connections until the end of time for this particular acceptor. And the way we can accomplish this is by injecting that events object, which has this interesting function next, context. And this is to help us solve the problem of distributing work. It's to help us solve the problem of distributing work in face of the fact that single-threaded code is really easy to write. It's easy to reason about, is correct by default. And so what we want to do is we don't just want to assign our incoming sockets to the same execution context the acceptor has. We want to bind different execution contexts into each incoming connection so that we can manage them in a single-threaded way on the associated execution context, while still taking advantage of the fact that our server probably has a lot of cores. And so async accept calls this, gets a reference to a context, and when it accepts, it binds that context into the associated socket. It associates that socket with that thread of execution, and then, of course, it needs to report it accepted a connection, and so it calls the accepted function, gives the endpoint, the remote endpoint of the socket, and injects the stream by moving it. Hands off responsibility to it, to the person they are calling. But having all these threads implies that we have some way of spinning up threads and managing them and giving them a context to run work in, and how are we going to do that? Well, we're going to write a thread pool. A thread pool which accepts a number of threads to its constructor and has a run function which allows us to surrender the foreground thread to run in the context. Not just to surrender the foreground thread, but also to spin up and run each of the necessary background threads as well. We also allow it to take a function which will be invoked on each thread which starts up in case we want to interoperate with some C library that requires something arcane like thread-specific initialization. Then we have a stop function we can call externally when we want our entire server to collapse and end. And since this is a pool, we need some way of actually looking at the things in the pool, so we have begin and end iterators so we can traverse it. But these are still just components. They're still just little pieces. And I promised you a running server. I promised you real sockets on a real network from real clients. So let's write the final piece of glue. Let's write that thing that you can call from main that actually gets us off the ground. Let's write run server, which takes in the configuration and takes in an events object. An events object which has two customization points. With pool, which takes in the configuration and the pool, and which allows us to glue in external components. It allows us to synthesize some state and then return it through that auto return value, and the caller is obligated to keep that alive for the lifetime of the application. This way we can spin up some state using the pool, and we can rest easy knowing that it will persist for the lifetime of the server. And then, because of that sticky problem of interoperating with C libraries, we have a function we invoke when each of our worker threads starts, which injects the context which is actually being run in that thread, and which we can use to do some thread local initialization. But this is just a function signature. What is the code we actually write to glue together our design? How complicated is that very difficult test of code which is going to reside in main? So let's walk through it. We're going to have many connections, and so each of them is going to need to have a state. And the user is picking which query gets serviced, so we're going to be templated on that. Our nested query type is going to be a verbose query, which is templated on the user's query type, and something called a connection description, which is just a wrapper of a remote and local endpoint, which supports being streamed to standard streams. Then we have a query driver type, which is just a template with some obligatory template parameters filled in. And we have a constructor which takes in the socket, which is the most important part, the local and remote endpoints, the user's configuration, and the user's with pool object, which we're going to pass through so that our implementer of our query can access them, so they can reach out to that state they prepared and incorporate it into their query. Then we have our query driver, and we have a sticky cancel waitable timer for the heartbeat operation. The impetus here is the same as the last time you made something sticky. When we cancel, we want cancellation to stick. We not only want to end all the currently outstanding operations, we want all future operations to fail as well. Then we have a vector of bytes, which is going to back the dynamic buffer that we're going to read into, and we have a done type, which couples that error code with the actual reason we're shutting down, with the failure reason that came from the first sub-operation to fail. And of course, we wrap this up in an optional and stick it in our struct because most of our connections spend most of their time not shutting down. Which brings us to the logic we're going to run when one of our operations ends. The logic that's going to fan in those operations and appropriately clean us up. We take in an R value reference to a shared putter, but this doesn't have to be a shared putter. We're just using it because it manages stable memory, which we need, and because it has a reference count, which we also need because we need to keep track of how many of our operations have completed. We take in the error code and we're templated on the reason enumeration. We populate the result if it's not already populated, filling in the reason that we're shutting down. Then we abort the query driver and cancel the heartbeat timer, which causes any outstanding asynchronous operations to come crashing down, to very rapidly fail, kick out, and call this function in turn. Then we check the shared putter, and if we're the last user, if the use count is 1, we need to proceed to the bottom of the slide and clean up. But if the use count isn't 1, we need to not clean up because we're going to let the last operation to complete do that, and so we throw away our count and return. If, however, we're the lucky final operation, we use the verbose wrapper around the query to just write out the timestamp and then write out the description of the connection and say we disconnected due to some failure. Because we want to expose our users to maximal context, we then write this anonymous class which visits our two reason enumerations and will format them in the elided code. We then visit this visitor, we write out a colon, and we also expose the user to the actual reason for the failure. Which brings us to managing states for our accepting sockets. Because we're a modern application, we want to be able to listen on IPv4 and IPv6 and on multiple endpoints. And so we're going to need to have a few of these. Our accept state just takes in the associated execution context and the local endpoint to listen on. Then it opens the acceptor, sets the reuse address flag, binds the local endpoint, and calls listen, thereby beginning to accept incoming connections. Note that we also add, as a member of this struct, the spot where we're going to store the remote address for each subsequently accepted connection. Now that we're armed with these two types, we can go and we can actually write the function we set out to write. We can actually get our server off the ground and start serving actual clients. And so the first thing we do is we're going to create a thread pool. We're going to create a thread pool with the configured number of threads, and then we're going to go off and we're going to call that with pool function. And since we promised we would, we're going to keep that object alive until the end of the server's lifetime. Then we prepare a list of our accept states and we loop over each endpoint we're configured to listen on. We log for each of them that we're going to start listening. We emplace a state in our list, and then we prepare a lambda whose definition has been elided for the moment. Then all we need to do is kick off that async accept operation. That operation which never succeeds because it's going to handle each and every incoming connection. We pass in the acceptor and the remote, and we pass in something called an async round-robin events, which is something that satisfies the name type requirements placed on the events object to async accept, which round robins over the iterators given, which are just iterators into the pool, and which invokes some lambda when it actually accepts the connection. And so we move in on accept. Then all we need to do is provide a completion handler for when and if that operation ever actually fails. Async accept is one of those operations that rarely fails, but hey, it could happen. And when that happens, we write to std error, there was an error, and we also dump the context of which accepting socket experienced that failure, and then we throw a system error. And throwing a system error in the completion handler of an asynchronous operation causes it to just bubble all the way up, be re-emitted from run on the thread pool, get caught at the highest level of the application, get dumped to the user, and call the application to end. Which leaves us wondering what we need to do whenever we accept the connection. How do we implement that on accept lambda? And the first thing we want to do is we want to transition to the correct execution context. Because as I said earlier, async accept is going to try to bind a fresh execution context into each accepted stream. But because of the way ASIO's asynchronous operations work, we're in the acceptor's execution context. And so if we want to write that beautiful, easy to reason about, correct by default single-threaded code, we need to place ourselves in the correct context. We need to place ourselves in the execution context, which is actually going to process this connection. So we get the executor out of the stream, we use ASIO execution execute to transition to that stream, and then once we're in the correct execution context, once we can proceed knowing we're data race free, then we start doing the actual work of kicking off all the operations on our connection. The first thing we need is to prepare its connection state, and so we make a shared pointer thereto. Then we dump out the timestamp using the query, and we write out that we accepted a connection from the remote to the local. Then we need to start the control operation, and so we call that function. We pass in the stream, and we pass in a dynamic buffer, which is not only backed by the buffer associated with this connection, but also has injected into it configuration about the maximum number of bytes it's willing to allocate. So we know we can't have someone drive by and denial of service us by just sending us 4 bytes with all bits set to 1. Then we make an async control events ref, which points to the driver, and we pass in a completion handler, which just calls the done function on our connection state. Which leaves us keeping that connection active, which leaves us starting off the heartbeat loop. And so we call async heartbeat. We pass in the stream, we pass in the write state it's going to use to prepare its header, we pass in the heartbeat timer, and we pass in a query driver async heartbeat events, which uses the query driver for some parts of the implementation, but also has injected into it the heartbeat interval, the maximum amount of time the connection is allowed to remain idle for. For the completion handler, we just inject essentially the same thing. It just calls done on the putter. The only difference is that it captures by move rather than capturing by copy, because we don't need that putter anymore. That's one of the reasons why we grab a reference to the state at the top of the slide. So now we've set up a bunch of asynchronous work. We've set it up to run, but we haven't actually started it running yet. And so what we need to do to actually finish our job is we make a signal set. We make a signal set that handles SIGINT and SIGTERM because we want to be able to shut down gracefully in response to the normal signals. We wait for a signal to be received, and when it is, we say we're stopping, and we call stop on the thread pool. Then we tell our user, finally, we've actually started a real server, and we call run on the thread pool to allow all that asynchronous work we set up to run. We call run, and we inject into it a lambda, which fulfills the last promise of this function, which calls thread start on our events object from each thread so they can go off and do that arcane C thread local initialization if they want to. And this case study, this tour through this server, hasn't just been me getting up in front of you and telling you that here's something I imagined might work. Here's something I thought of. Here's an idea that I had. Because the design and all of the code on these slides isn't just an idea. It's actually embodied in an actual repository, which is compiled and built and deployed, which is running in production right now, which, while I've been giving this talk, has doubtless serviced many thousands of queries. Are there any questions?
Why did you use a toggle and not a queue for maintaining a buffer of text to write on that network connection?
The question was why I used toggle rather than using a queue. I guess queue could be a valid implementation, and I'm just trying to think if someone could implement, because it's a type requirement, if someone could implement toggle using a queue. The only reason I wouldn't want to use queue on the front end is because then that would couple me to a certain data structure. I can't think of off the top of my head why you couldn't have toggle through a queue of buffers, but I think async control might be implemented to assume there's only 2. So if it fills the back buffer, it just stops. And one of the reasons for that actually, for stopping, I mean, I can imagine extending the concept so that you could eject this logic. The reason for stopping and not filling more back buffers is because you don't want to get in a situation where your user is receiving data from you, and kind of in the vein of the dynamic buffer thing, they're just like, I'm just going to let the TCP window slam shut. And then the operating system's like, okay, I'm just going to wait and not send, and you're just allocating a bunch of memory, filling up buffers you're never going to send from the hard drive. But other than that, like, there's no reason fundamentally why I shouldn't or couldn't adjust that concept. So the user can inject that, be like, no, back off, right? I don't want to allocate anymore. Because then they could just say, I only want to have a front buffer, for example. Any other questions? The question was how I can add TLS support to this. And the answer to that question is that, so in the last bit that I showed, or the very last bit, the run serverless implementation, the answer to that is I can't, right? And because that run serverless implementation indicates a set of choices I've made, a concrete set of choices. But throughout the whole rest of the design, right, the whole rest of the design leading up to those final slides where I was implementing run server, all I trafficked in was async write stream, async read stream, and async stream. So I just need something that modeled that named type requirement. And if you open up, not the networking TS, but you open up the parts that ASIO extends the networking TS to include, there's an SSL stream. Right? So someone could connect that SSL stream, do the async handshake, and then inject that into the whole datacon framework, and all of a sudden it magically speaks TLS. That was actually something that I did internally to our company when we were writing a fix engine, and the selling point was that because it was all ASIO-based, you could just be like, oh, here's an SSL stream, and all of a sudden you could talk to GDAX, which was like big at the time we were writing it. Like they spoke fix over the internet, over SSL, and no one else's fix engine could do that. So it's easy with the framework, but the run server would just need to be rewritten. And that's the whole point of run server. It embodies a set of decisions that you've made, right? And it's the concrete server that's going to run, and it only is customized on like query and with pool and configuration. Any other questions? Okay, well, thank you for coming. I'll wrap it up there.